Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 24, The Origin of Our Solar System. In our last lecture, we took a quick tour of the planets of our solar system. In this lecture, we're going to try and understand a bit better how the solar system came to be, at least our modern ideas for how we ended up with a solar system organized the way that it is. So you'll remember from the last lecture that the solar system consists of three types of bodies. There are the terrestrial bodies, Mercury, Venus, Earth, and Mars, the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, and then the cold, icy bodies out here. And they are arranged in the solar system. And this arrangement, turns out, is important for understanding how the planets got the way that they are, is that the hard, rocky planets are very close to the sun in the inner part of the solar system. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are quite spread out in the middle part of the solar system, and the cold, icy bodies are out here at the edge of the solar system. Now, here are the properties of the planets. We went over this chart last time to just say that you should not memorize this chart. I'm not going to ask you specific numbers off this chart. Mostly what we want to see on this chart are trends. And the trends that we're going to look for have to do with the density of the planets. And so we've got density over here. Density is simply a measure of how tightly matter is packed together. It's measured in grams per cubic centimeter. The density of water is 1 gram per cubic centimeter. So a density on this chart of 1 is the density of water. So you can see that in our solar system, most everything has a density greater than water. Saturn is the only thing that is less dense than water. And we'll come back and talk about those in a few seconds here. All right, so here are the planets in our solar system. Let's talk about the three categories of planets individually. So let's start first with the terrestrial planets, Mercury, Venus, Earth, and Mars. Mercury, Venus, Earth, and Mars, here they are to scale. So Venus is almost the same size as the Earth. Mars is about half the diameter of the Earth, and Mercury is about a third the diameter of the Earth. And so there are the terrestrial planets in our solar system. All of them are rocky planets. Mercury, Venus, Earth, and Mars are all made of solid rock. And that shows up in their densities. If we look at the average densities of these planets, Mercury is 5.4 grams per cubic centimeter, Venus is 5.3, Earth is 5.5, Mars is 3.9. Those are the densities that we typically find for rocks here on the surface of the Earth. A typical rock on the surface of the Earth here might have a density of 3.5 or maybe even 4 grams per cubic centimeter. So these are well within the realm of the density of rocks. And so all of these terrestrial planets are the rocky planets in our solar system. And we get that from their densities. And obviously from the fact that we have visited all of them with spacecraft and have confirmed that. All right, how about the gas giant planets? So here's the sun, and to scale there is the Earth, and here are the giant planets, Jupiter, Saturn, Uranus, and Neptune, the Jovian planets. So here are the Jovian planets with Earth drawn to scale down there. What are their densities like? Well, when we look at their densities are all about the same as the density of water, which is 1 gram per cubic centimeter. Jupiter is 1.3. Saturn is 0.7, Uranus is 1.2, and Neptune is 1.6. So all of these have densities that are just a bit denser than water, except Saturn, which is a little bit less dense than water. So they sort of all average out to around the density of water. So we've talked about the hard, rocky planets. We've talked about the gas giant planets. Now let's talk about the cold, icy bodies. As I've mentioned, out there at the edge of the solar system, there is the Kuiper belt of objects. The largest member of the Kuiper belt of objects is Pluto, and these are icy bodies. They are made primarily of water ice. And so they are denser than the gas giant planets, but not nearly as dense as the rocky planets. And they have an intermediate density. So in the case of Pluto, its density is about 2.1 grams per cubic centimeter. So again, denser than the gas giant planets, but not as dense as the rocky planets. So what we want to understand is how this arrangement came about. How did we get 4 rocky planets up close against the sun, 4 gas giant planets in the middle of the solar system, and then a whole bunch of cold icy bodies out there at the edge of the solar system? So let's do a quick tour of star formation, how we believe that stars, and in particular our sun, and the planets around it form. So the first thing to know is that stars are born from giant clouds of gas and dust called interstellar clouds. Now, these clouds contain primarily hydrogen gas. They are typically today about 74% hydrogen, about 25% helium, and about 1% everything else. And by that 1% everything else, I mean that's carbon, nitrogen, oxygen, iron, nickel, phosphorus, all those elements on the periodic table other than hydrogen and helium make up about 1% of the cloud. Helium is about 25% of the cloud. Hydrogen is about 74% of the cloud. So these clouds are dominated by hydrogen and helium gas. Now, these clouds can exist in the interstellar medium, the space between the stars, for millions, if not billions of years. But eventually, as they orbit around the galaxy, they will find themselves having gravity squeeze them tighter and tighter. Sometimes they will pass into a spiral arm in the galaxy, and that will squeeze them. Sometimes they will find themselves next to a supernova, an exploding star going off, and that will compress them. But typically there is some event that compresses this cloud to begin with, and once that compression begins, the cloud collapses to form stars and planets. Probably the best studied of these interstellar clouds is called the Orion molecular cloud. It gets the name Orion because it's in the constellation of Orion as we see it in the sky, and it's a molecular cloud because it is dense enough that most of the gas in the cloud is actually found in the form of molecules. It is cold enough and dense enough that hydrogen atoms bond together to make molecular hydrogen, and we see other molecules like water and methane and ammonia. All of these simple molecules are found in these giant molecular clouds. There are complex molecules found there too, but that's a different topic. All right, so let's talk about the Orion molecular cloud. First of all, let's identify Orion in the sky. Orion is the most prominent of the wintertime constellations. These stars form the head of Orion. These two stars form his shoulders. These three stars form his belt, and these two stars form his knees. And you'll notice that his belt doesn't go straight across, but it's tilted because there's a heavy sword hanging off the side, and that sword is pulling his belt down. Now, this is what Orion looks like in visible light. This is what we see with our eyes: the brilliant reddish-orange star Betelgeuse, the blue-white star Rigel, the three famous belt stars of Orion cutting across the middle, and this little pinkish star down here, which is not a star at all, we'll find out in a minute, is actually one of these giant star-forming regions. But if we could see in the infrared portion of the spectrum, a kind of light beyond the red end of the spectrum, this is what we would see when we look at Orion. So we would see Betelgeuse right there. Most of the other stars would disappear in the infrared, but then we will see two giant glowing clouds of gas, and primarily in this case, in the infrared, we're seeing the dust. Although these clouds are dominated by gas, in the infrared, the glow that we see mostly comes from little tiny particles of dust that are just a few tens of degrees above absolute zero, but they are warm enough to glow in the infrared portion of the spectrum and show up brighter than the blackness of cold space. So there are two giant clouds right here, one in the sword of Orion and one right there in the belt of Orion. And we're going to talk about this one in the sword down here. That is the Orion molecular cloud. So it's about 1,500 light years away from us, which means the light left about 1,500 years ago. The light that we're seeing today is 1,500 years old. The cluster itself, or I should say the cloud itself, is about 100 light years across, and it contains enough material to make 430,000 stars like our sun. Now, it turns out that our sun is more massive than your average star. So this cloud will actually probably end up making more stars than that. On the other hand, star formation is not terribly efficient, and a lot of that mass will not get turned into stars. So this cloud will probably end up making hundreds of thousands of stars, but most of them will be lower mass than our sun. And this cloud is also famous because it contains the Orion Nebula and the Horsehead Nebula. So let's look back at Orion again here. So here's the head of Orion, his two shoulders, the belt stars, his two knees down here, and the belt is tilted because there's that heavy sword hanging off the side. If we take a photograph of this part of Orion, this is what we see. Here are the three belt stars of Orion right there. There's a giant cloud of gas and dust around this belt star, and that is where the famous Horsehead Nebula is located. And then in the Sword of Orion, there is this giant star-forming region down here called the Orion Nebula. To put this in perspective, there is that photograph on the constellation of Orion. So there are the three belt stars, and there is the Orion Nebula. Now, it turns out these giant clouds of gas and dust contain lots of molecules. I mentioned earlier that's why they're called molecular clouds. And they also contain lots of dust. If we look at these clouds in the light that's given off by dust particles, this is what it looks like. And these images are to scale. That is, these are exactly the same scale. And now you can see how big these two giant dust clouds are in this part of Orion. In fact, they're bigger than your fist held out arm's length. They're more than 10 degrees across. If you were to go out, if you had infrared eyes, and you could look up in the constellation of Orion, you would see this giant glowing cloud of dust up there in the sky. In terms of molecules, there are carbon monoxide molecules inside this cloud that emit radio waves, and we can study the molecules inside the cloud by studying those radio waves. But let's study in particular the Orion Nebula right here. So we'll focus our attention here on the Orion Nebula. So the Orion Nebula, here's a photograph of it. It's one of the most beautiful objects to photograph in the sky. Unfortunately, the sun is in that part of the sky here in the summer of 2020. The sun is in that part of the sky right now, so you can't really photograph it with the RRRT. But if it's a different time of the year, especially if it is the fall or winter, you can use the telescope to take a photograph of it. It looks really quite beautiful. So deep down inside this Orion Nebula, there is a cluster of newborn stars called the Trapezium Cluster. And the Trapezium Cluster is about 1,530 light years away from us. So it takes light 1,530 years to get to us. The cluster itself is made up of about 1,800 stars, 1,800 stars. The average age of the stars inside the cluster is less than 1 million years, and some of them are as young as a few 100,000 years. And the most massive of the stars, one that we'll talk about here in a second, has a mass that is 36 times the mass of our sun. It has as much mass as 36 stars like our sun, all combined into one star. All right, so if we take a close-up look at the center of the Orion Nebula here, so we're just going to look at this central brighter part. You'll notice sort of a flat edge right there and a flat edge right there. So let's blow up this inner part of the Orion Nebula right there. And there's that inner part of the Orion Nebula. And then we see these four stars down here at the center, and they're called the trapezium. They get their name from the fact that they're in the shape of a trapezoid, sort of a tilted square right there. And those are the four stars that are 1,530 light years away from us. Now, this is an image taken from a ground-based observatory. It was taken at Lowell Observatory in Flagstaff, Arizona. And it was taken by a 1.8 meter telescope. That is a telescope that has a mirror that's 1.8 meters across. But what I wanted to show you was this exact same photograph, but taken with the Hubble Space Telescope. So the Hubble Space Telescope has photographed this part of the Orion Nebula. And what you'll see is that it looks much sharper because the Hubble Space Telescope is above the blurring effect of the Earth's atmosphere. So here is a ground-based photograph of the center part of the Orion Nebula, and here is a Hubble photograph. So look at the difference between the two. And look at just how much sharper and clearer the Hubble Space Telescope photograph is. Now, it's not that the ground-based telescope was out of focus. It's just simply the blurring effects caused by the Earth's atmosphere. Now, I mentioned that this region has about 1,800 stars in it. I said that the trapezium cluster consists of about 1,800 stars. And looking at this image right here, you might wonder, where are all the stars? Well, the answer is most of the stars are buried so deep down inside this molecular cloud that we can't see them in visible light. There's enough dust that the visible light from these stars gets absorbed before the light gets to us, and we can't see them. But if we look in infrared light, which has a longer wavelength, infrared light can penetrate through that dust, get all the way through the dust so that we can see it. So, as a reminder, here's a ground-based image of the Orion Nebula, the center part of the Orion Nebula. Here's a Hubble Space Telescope image to exactly the same scale. Here is a Hubble Space Telescope infrared image of the center of the Orion Nebula, and that's what it looks like. And in fact, if I flip back and forth between them, you can see the stars lining up right there. So if you look at these two stars right here, They are the same as these two stars right there. There's a little triangle of 3 stars right here, and that is this triangle of 3 stars right here. So you can see that they line up. So these are the stars of the trapezium. And now you can see many of the stars that are buried deep down inside this giant star-forming region. But most interestingly of all, look at this thing right here. Right, so here is the trapezium, those 4 young hot stars that are at the center of the Orion Nebula. But when we look just above it and to the right, we don't see anything at all in visible light. But in infrared light, we now see a huge, massive star-forming region buried deep inside the cloud, buried so deep inside the cloud that we can't see any evidence of it in visible light. Okay, so that is just a little bit about the Orion Nebula. Now, with the Hubble Space Telescope, we can photograph some of these newborn stars, especially the ones that are on the near side of the cloud so that there's not much dust blocking our view of them. And what observations with the Hubble Space Telescope have shown is that about half of all these newborn stars are surrounded by disks of material. So if we look at some of them, here are pictures of 4 of these newborn stars taken with the Hubble Space Telescope. So at the center of each of these, you see the newborn star. But surrounding them, you see a dark disk of material. And that dark disk of material consists of gas and little tiny particles of dust and rock and ice. And those are called protoplanetary disks. And it is those protoplanetary disks that are eventually going to form planets. So as I mentioned, these disks are a mix of typical interstellar material. There's lots of hydrogen and helium in gaseous form. There are little tiny grains of ice and little tiny grains of dust or rock, solid particles. And those solid particles contain most of the heavy elements, things like iron and nickel and silicon. The ice contains, it's mostly water ice, it's hydrogen and oxygen, but also some methane ice, frozen carbon dioxide, frozen carbon monoxide, frozen ammonia, other ices in addition to water ice. And the disk typically contains between 1 to 10% the mass of our sun, and that is more than enough material to form the planets that we see in our solar system. All right, if we were to see these disks edge on, so we're seeing these disks sort of face on like this, if we were to see them edge on, they would look like this. So here are 2 of these disks photographed with the Hubble Space Telescope in Orion, seen edge on. In this case, the newborn star is completely hidden down inside the disk, and in this case, the newborn star is just peeking up above the top of the disk of material right here. So these are the disks that are forming planets. So what happens to the dust and the ice in here? Well, let's talk about those dust particles for a second. Those dust particles are really quite complex. They're microscopic. They're about the same size as the dust particles that are released when someone smokes a cigarette. When someone smokes a cigarette, you'll often see this blue hazy cloud coming off the cigarette. That blue hazy cloud consists of little tiny particles of soot, of dust. And they are similar in size to the little tiny particles of dust that we find out there in the interstellar medium, the space between the stars. So this is what those grains of dust look like. This particular grain of dust, by the way, was captured by a NASA aircraft. It flies, it's an old retired U-2 spy plane, and it flies at very, very high altitudes. And when they get it up to very high altitudes, they literally lift out a sticky collector, and as little tiny particles of interstellar dust float down through our atmosphere, they collide with this sticky collector and they get collected and brought back down to the ground and analyzed. So early on, these little tiny dust grains, they're so complex that when they collide with another dust grain, they often stick together. And they eventually form little clumps of material, and those clumps stick to other clumps, and this continues building up. So we start with little tiny grains of dust, and they collide with other grains of dust to make bigger clumps. Those bigger clumps collide with other clumps to make even bigger clumps. And this keeps going on until they get to the size of what we would consider today to be asteroids. We call them planetesimals, objects that are the size of small moons in our solar system today. So these little tiny grains of dust stick together till they make clumps. Those clumps collide with and stick to other clumps until we get planetesimals. And then planetesimals are now the first really big solid bodies in the solar system. They're large enough that their gravity actually begins to pull more stuff in. So up until this point, gravity wasn't really playing a role in planet formation. The things were just literally colliding and sticking together. But now that we've got planetesimals, the things that are the size of asteroids in our solar system, now their gravity is strong enough to start pulling material in. These are some of the asteroids in our asteroid belt that have been photographed up close by a variety of spacecraft. Some of the spacecraft were headed to the outer solar system. Some of them were sent out to the asteroid belt in particular. And I should mention, these are not asteroids down here, but these are comets down here at the bottom. So there's Halley's Comet, for example. And these are all shown to scale. So it shows you the sizes and the colors of these asteroids to scale. But back to our planetesimals. So planetesimals are made of the solid materials in the disk. They're made of the little tiny pieces of rock and dust. And they're made of ices as well. And they're mostly made of all the elements other than hydrogen and helium. Now, in our solar system, billions upon billions of these planetesimals formed in the solar system. And these planetesimals collided to make the larger planets. And this process of small particles colliding to make bigger particles, colliding to make bigger particles, colliding to make planetesimals, colliding to make the planets, it's called accretion. And that is how the planets in our solar system grew. So by about 100 million years after the formation of our solar system, which is very quickly, our solar system, as we'll see at the end of this lecture, is 4.6 billion years old. It only took about 100 million years for most of this material to get swept up in the big planets to form the large major planets in our solar system. But some of those planetesimals were left over. Those are the asteroids and the comets that we see today. But in that first 100 million years, a lot of that material was swept up. And the evidence we have for this is looking at the ancient surface of the moon. Later on this semester, we will talk about the moon as a fossil. The fact that because there is no atmosphere, the surface of the moon preserves the history of our solar system for billions of years. And when we look at the oldest parts of the surface of the moon, we see that it is completely covered in craters. And what we're looking at here is the end of planet formation. We're looking at the clearing out of the solar system when all these planetesimals were being accreted onto the giant planets, making on the surface of the moon thousands upon thousands of giant craters on the surface of the moon. In fact, the moon itself is an example of accretion. The moon itself was made when a giant Mars-sized body struck the Earth 4.5 billion years ago, and the material that was blown out from that impact ended up forming our moon. But we'll learn more about that later on when we talk about our moon. And this process of accretion continues even today. If you've ever had the chance to go out and watch a meteor shower, as you watch meteors streaking across the sky, you are seeing little tiny particles of ice and dust burning up in the Earth's atmosphere, adding to the mass of the Earth. So that's what's going on in a meteor shower. All right, back to our solar system. So how did we get the solar system that we have today? How did we get the hard, rocky planets on the inside, the gas giants in the middle, the cold, icy bodies on the outside? How did it come from this process of accretion? Well, I want you to think about taking one of these nebulas that's made primarily of gas, hydrogen and helium gas. You've got some oxygen gas, carbon gas, things like that. And as it starts cooling off, what are the first things to condense out of this cloud? So what I want you to do is I want you to rank in order that these things will condense. I want you to rank these four things: rocks, ice, gas, and metal. What order will they condense as the solar system forms? So I want you to start with the material that will condense first and end up with the material that will condense last. And by condense, I mean go from the solid phase, go from the gaseous phase to the solid phase. That is, if you imagine water vapor in space freezing and becoming solid water ice, that is the water vapor condensing to form ice. So go ahead and go out to learning catalytics for a few seconds, and I want you to rank these four things: rocks, ice, gas, and metals, in the order that they will condense. So take about 10 seconds to do that. All right, so what did you get when you did that? So what you should have gotten is that thinking about the temperatures at which these things vaporize. That is, let's work backwards. Let's start with rocks, ice, gas, and metals. and figure out what temperatures it takes to turn them into a gas. Well, gases like hydrogen and helium are already a gas at room temperature. So those will not condense into a solid until it gets very, very cold. Even at room temperature today, it's not cold enough for hydrogen and helium to condense into solids. It is possible just a couple degrees above absolute zero to condense hydrogen into a solid. But helium would have to be cooled to a tiny fraction of a degree above absolute zero. We can make liquid helium at a few degrees above absolute zero, but we don't make a solid out of it. So now let's start heating this up and see what happens. Well, the first thing after gases that are going to turn into a gas are ice. Ice will be the first thing to vaporize. And so as we play the record backwards, or play this example backwards, when things are condensing, the second from last thing to condense will be the ices. And then if we have the rocks and the metals right here, well, metals have a higher point of vaporization. You have to heat a metal up much hotter than a rock to get it to vaporize. So the rocks will vaporize next and then the metals, which means in terms of condensation, the metals will condense first, and then the rocks, and then the ices, and then the gases. So what does this have to do with the formation of our solar system? Well, it turns out that the local temperature of our solar system, the temperature at any given location, determined what materials existed as solids. In the inner part of the solar system, where it was really hot, sort of 500 to 2,000 degrees, the only thing that could exist as solids were metals and rocks. And that is why the inner planets are primarily made of metals and rocks. And then in the intermediate part of the solar system, where the temperature was sort of 100 to 500 degrees, and by the way, these temperatures are in Kelvin here. The temperature was 100 to 500 degrees Kelvin. Water ice could exist, and metals and rocks. And so those planets could not only build themselves up using metals and rocks, but could also build themselves up using water ice. And then finally, out there at the very edge of the solar system, where it was very cold, only 20 degrees to 100 degrees Kelvin, methane ice and water ice and a little bit of metals and rock existed. So here's a plot that shows us very roughly the distance from the sun and the temperature of the nebula as the planets were forming. So here in the inner part of the solar system, it was quite hot. It was between, say about 500 to a few thousand degrees in the inner part of the solar system. And that meant the only thing that could survive in here were metals and rocks. And that is why Mercury, Venus, Earth, and Mars are primarily made of metals and rocks. In the middle part of the solar system here, the temperature was between a few tens of degrees to a few hundred degrees. In this part of the solar system, we had not only rocky materials and metals, but we also had water ice and ammonia ice. And so these could be built up not only with rocks and metals, but with ices as well. And in particular, we call this line right here the ice line in the solar system. Beyond this distance, further out in the solar system, ice can exist as a solid. Inside that line, it's too hot. The ice will vaporize into a water vapor. But here is the ice line. And you'll notice where Jupiter is in our solar system, and Saturn, and Uranus, and then Neptune further out. They are all out here where there was lots and lots of ice. And then finally, way out here at the edge of the solar system, way off the graph out there, we have the icy bodies, Pluto. So the hard rocky planets formed in the inner solar system because that's all there was for them to form from. Those rocky planets, as those planetesimals collided, there was no ice that they could gather up. There was no hydrogen and helium. It was just too hot in the inner solar system. So the temperature in the solar nebula determined the composition of the planets. Close to the sun, objects are made of metal and rock. Far from the sun, objects are made mostly of ice with some metal and rock. And let's talk about how the gas giant planets got the way they are, because we haven't really talked about hydrogen and helium much yet. And in any case, it was never really cold enough in the solar system for hydrogen or helium to exist as a solid. So where did they come from? Well, in this giant collapsing cloud of gas and dust, there was lots of hydrogen and helium around. And the Jovian planets, the giant planets, they started as icy, rocky seeds. Rocks and metals and ice clumped together. But because ice was much more abundant than rocks and metals, these things could grow much faster than any of the terrestrial planets. So the giant planets like Jupiter and Saturn, Uranus and Neptune, they started with these icy, rocky cores. because they were growing in an area that was rich in ice. And they grew with all this ice so big and so fast that they became sufficiently massive that their gravity could start pulling hydrogen and helium gas out of the nebula. And today, their masses are dominated by all that hydrogen and helium gas that they pulled in. And deep down at the center of Jupiter, we don't know exactly what's down there, but we certainly know that it is hot enough today that icy materials do not exist as we would consider ice. In fact, the temperature at the core of Jupiter is hotter than the surface of the sun. It's not hotter than the center of the sun, but it is hotter than the surface of the sun. So ices do not exist down at the center of Jupiter, at least ices as we think of them today. But they do have some kind of core down there. It may not be solid. As I say here in the slide, it's probably slushy, but it is made of those heavy elements that used to be the rocks and the ice that formed early on. So that raises the question, when did our solar system, and let me finish before I talk about when, let me say about Pluto. So Pluto and those other planets, they formed primarily of ice. It makes sense, right? They were out here in the outer part of the solar system where ices primarily exist. Question is, why are they so small? And the answer is they formed out here at the very edge of our solar system. If I go back to this slide for a second, they formed out here at the edge of the solar system where the solar system was really just running out of material. There wasn't enough material left over to form a lot of giant bodies. Now, many of the bodies in the Kuiper belt, Pluto and those types of bodies, were actually probably formed a little bit further in the solar system, around the areas of Uranus and Neptune. And the gravity of Jupiter, Saturn, Uranus, and Neptune flung those bodies out into the outer part of the solar system. So we'll talk more about that later on in the semester. Okay, so the question then is, when did all this happen? Now that we have a good idea of how the solar system formed, when did the solar system form? Well, the way that we determine the ages of things is using through the radioactive decay of elements. Certain elements on the periodic table of elements, for example, uranium, are radioactive and they decay. And a radioactive element, we call it the parent, decays into a daughter element. And sometimes there's intermediate steps involved. So uranium, for example, over time decays into lead. There are some intermediate elements that are made along the way. But the decay of radioactive elements is a statistical process, and it is extremely reliable when it comes to measuring the ages of objects. The half-life is defined as the time that it takes half of a sample of the parent element to decay into the daughter element. So again, uranium would be the parent element, lead would be the daughter element. It's what uranium eventually decays into, and the half-life is simply the length of time that it takes for half the uranium to decay away. And over time, it turns out you can use the ratio of parent to daughter, or daughter to parent, I should say, to determine how old something is. So let's use an example of this. Let's take a radioactive element here. So we have a radioactive element, and the parent is represented in the red, and the daughter is represented in the blue dots right here. When the rock is brand new, let's imagine that it consists 100% of the radioactive parent element. Over time, that parent element decays. So if it is 100% parent element at the beginning, over time it decays to 75%, 50%, 25%, and on down. Well, you'll remember the half-life is defined as the length of time it takes for half of the atoms to decay into the daughter. So the half-life here, this is one half-life right here, because now the parent went from 100% to 50%. At the same time, the daughter went from 0% to 50% because all of these atoms that decayed eventually became the daughter atoms. So now we have half of the parent and we have just as much daughter as parent. After another half-life goes by, half of the atoms that we have decay. And that's an important distinction to make. Every half-life, it is half, not half of the original atoms decay, it is half of the atoms that you have remaining. That's what we mean by a statistical process. Whether an atom decays or not is a statistical process. It's not that they have an expiration date or that they're going to decay by a given date. At any given moment, an atom may or may not spontaneously decay. And as I said, it's a statistical process. And that's why when we reach the 50% point here, after another half-life, half of these will decay. So by the second half-life, we went from 50% down to 25%, and now it is 75% daughter. After another half-life goes by, now we're down to 12.5% of the parent and 87.5% of the daughter up there. Okay, so what elements do we use to do this? Well, fortunately, there's a lot more than one radioactive element to do for this, and all of these elements that I show you here are used for determining the ages of rocks and therefore the ages of continents on Earth or planets, asteroids, comets in the solar system. We'll talk in a minute about that. So one of the ones that is used most often here on Earth is the decay of potassium. An isotope of potassium decays into an isotope of argon, and that has a half-life of 1.25 billion years. There's a form of rubidium that decays into strontium with a half-life of 48.8 billion years. Samarium decays into neodymium with a half-life of 106 billion years. That's really quite incredible. The universe isn't even that old. Lutetium decays into hafnium with a half-life of 35 billion years old. By the way, the universe is 13.8 billion years old. It's about 14 billion years old, but 13.8 billion years old. Remember that from the first lecture, or the second lecture. Rhenium decays into osmium with a half-life of 43 billion years, thorium into lead, uranium into lead. And here are two different kinds of uranium, two different isotopes of uranium. Uranium-235 decays into lead-207 with a half-life of 700 million years. And uranium-238 decays into lead-206 with a half-life of 4.5 billion years. Now, here's an interesting question. I don't know if you've ever thought about it. How do scientists measure the half-life of an element? In particular, let's imagine samarium here, which decays into neodymium with a half-life of 106 billion years. We haven't been around that long. How can we, it's not like we take a sample of samarium and wait 106 billion years to see half of it decay. Or let's use lead down here. Uranium-238 decays into lead-206 with a half-life of 4.5 billion years. Humans haven't been around for 4.5 billion years. We can't have waited for half of it to decay. So how accurately do we know these half-lives? Well, it turns out we know them quite well. And the reason is you don't have to wait 4.5 billion years to determine what the half-life is. In fact, all you need to do is take a sample of atoms and know how many atoms you have and count how many of them are decaying. And from the rate at which they're decaying, you can figure out how long it's going to take half of them to decay. Let me give you an example. So imagine that I have 1 gram of pure uranium-238. How many atoms do I have? Well, you might remember from high school chemistry class that this is the value of Avogadro's number. Avogadro's number, that famous number that tells you how many items are in a mole, tells us the number of atoms in a mole, and that's 6.022 times 10 to the 23rd. Now, atomic mass tells us the number of grams in a mole. So for uranium-238, which has an atomic mass of 238, that means that 1 gram of uranium-238 contains 6.022 times 10 to the 23rd divided by 238, or 2.530 times 10 to the 21 atoms. So if I just took 1 gram of uranium-238, I'd have 2.5 times 10 to the 21 atoms in there. Now, I could take that 1 gram of uranium and I could surround it by radiation counters, and I could count the number of atoms that are decaying every second with the radiation counters. And from that, since I know how many atoms I have and I know how many are decaying every second, I can calculate how long it will take for half of them to decay. And so, for example, in my 1 gram of uranium-238, with that many atoms, on average, about 9,000 atoms are going to decay every second. And with 9,000 atoms decaying every second, in 4.5 billion years, about half the sample will have decayed and only half the sample will be left. That is, about half the sample will be uranium still, and about half the sample will have decayed into lead. And that means that the half-life is 4.47 billion years. So let's use an example for the solar system. Let's use the decay of potassium-40 into argon-40 as an example for telling how old a rock is. Now, potassium-40 to argon-40 is a really interesting one because argon, you'll remember, is a noble gas. So when a rock is molten, when it's liquid form, like if you think of liquid lava, all the argon that's in that rock, or much of the argon that's in that rock, will actually leave the rock. Because it's a gas, it will bubble out of the rock. And argon doesn't form molecules. It doesn't form minerals. And so most of that argon will be lost out of the rock. So when that rock solidifies, there will be some radioactive potassium-40 in there. Now, the potassium-40 has a half-life of 1.3 billion years. So we form this new rock. It's got some potassium-40 in it. Argon's a noble gas. It's not going to form minerals in rock. So typically, any argon that we find in the rock is going to come from the decay of potassium-40. And once that rock solidifies, that argon doesn't really have a way to get out. So what's going to happen in our rock? Well, we're going to start with 100% potassium-40 and no argon-40. And after one half-life here, 1/2 of the potassium will have decayed. So now we will have only 50% of the potassium that we had earlier. And all that potassium that decayed will be argon. Now, and that's going to happen at one half-life, which is 1.3 billion years. So that's when the rock is 1.3 billion years old. Another half-life goes by. So half of the remaining potassium atoms will decay. So now we'll have 1/4 of the potassium atoms that we have before. And all of those potassium atoms will become argon-40 atoms. And so now we will have 75% argon-40, 25%. And that's after 2 half-lives, which is 2.6 billion years. After 2 more half-lives, we would just see the potassium-40 keeps decreasing and the argon-40 keeps increasing there. Okay? So that is another example of how we do it in rocks. So let's put this together and let's do some examples of this. Well, we'll continue this and then, so after 3.9 billion years, which is 3 half-lives, so that's right here. This is the 3rd half-life right here. There's going to be 1/8 as much potassium as there was at the beginning. And there'll be 7 times as much argon as potassium. And if we take a rock today, all we have to do is measure how much argon-40 is in the rock and how much potassium-40 is in the rock. And the ratio of daughter to parent tells us how old the rock is. Now, we'll want to double check that work, and that's the advantage to having many different radioactive elements that we can use, because we don't have to just use the decay of potassium to argon. If that rock has some uranium in it, we can use that as well. Or if it has some thorium or samarium or lutetium, we can use any of those in addition to the potassium and argon. And that gives us multiple elements to cross-check the results. So let's do some learning catalytics examples. Let's do the first one. Assume that you have a sample of 100 milligrams of element X, which is the parent, that decays into element Y, the daughter, with a half-life of 30 million years. After 30 million years, how much of element X do you have? So we start with 100 milligrams of element X. 30 million years go by. How much of element X do you have after 30 million years? So go to Learning Catalytics and answer that question. All right, what did you get on this one? So let's start making a table here. We're going to make a table here. This is the age. Sorry, I should have properly written millions of years on there. So this is the age in millions of years. So this is when the rock is new formed. When it's brand new formed, its age is 0. We have 100 milligrams of element X. We have no milligrams of element Y. After 30 million years, which is 1 half-life, half of X has decayed. And so X has gone from 100 milligrams to 50 milligrams, and Y has gone from 0 milligrams to 50 milligrams. This 50 milligrams all came from this. That was the 50 milligrams that disappeared right there. And the ratio of daughter to parent is 1:1. All right, so now I want you to answer this question. Assume that you have a sample of 100 milligrams of X that decays into Y with a half-life of 30 million years. That's the same as the last question. After 60 million years, how much of element Y will you have? Now read this question carefully. After 60 million years from the beginning, how much of element Y do you have? Element Y is the daughter. So go ahead and work that out. Spend a few minutes, go out to Learning Catalytics and answer that question. Okay, so what did you get for that one? Let's take a look. So when it is 60 million years old, Of that 50 milligrams, another half-life goes by, because remember the half-life is 30 million years. So in this half-life, half of the remaining atoms have decayed. So now we have 25 milligrams of the parent and we have 75 milligrams of the daughter right there. So the answer to that one was 75 milligrams. Now answer this one. Assume that you have a sample of 100 milligrams of X that decays into element Y with a half-life of 30 million years. That's the same as we've been doing before. After 120 million years, how much of element X will you have? So after 120 million years, how much of element X will you have? All right, what did you come up with this one? This one was a bit tricky because there was an extra half-life in there, and that was this half-life here. So when it was 0, we had 100 milligrams. At 1 half-life, it was cut in half. At 2 half-lives, it's cut in half again. At 90 million years, which is 3 half-lives, it's cut in half again. And by 120 million years, it's 4 half-lives. It is divided all the way down to 6.25 milligrams of element X. Element Y over here will make up for that difference. So element Y is now 93.75 milligrams. And that just comes from all of element X that has decayed, has gone into the daughter Y right there. Now, how do we typically do this in science? Well, what we typically do in a rock is we measure how much Y we have, we measure how much X we have, and we look at the ratio between the two. So in this case, for example, the ratio of daughter to parent was 1:1. The ratio of daughter to parent is 3:1. The ratio of daughter to parent is 15:1. So the question I have is this. Assume that you have a sample X that decays into Y with a half-life of 30 million years. Your sample has 7 milligrams of element Y for every milligram of element X. How old is the sample? So there's 7 milligrams of Y for every milligram of X. How old is the sample? So go ahead and take a few minutes to answer that question. All right, welcome back. If you look at the previous table, the answer to that is if the ratio of daughter to parent is 7:1, then the rock must be 90 million years old. So the age here is 90 million years. So from studying the decay of radioactive elements, what have we determined? Well, we've directly analyzed rocks from the Earth. We have brought back rocks from the moon. We have on Earth meteorites that we are quite confident came from Mars. And then we also have lots of meteorites that came from the asteroid belt and other places in the solar system. So we have directly analyzed all of these rocks. So what have we found? We have found that the oldest Earth rocks are 3.8 to 4 billion years old. Now you might say, well, that sets the age for the Earth, but that doesn't necessarily. And here's the problem. Earth rocks get worn down by erosion over time. So just because the oldest Earth rocks are 3.8 to 4 billion years old doesn't mean that there weren't rocks before that have all just been worn away. And the evidence that we get for that is that some Earth rocks contain little tiny crystals of zircon. Now, zircon is a really, really tough material, and it can last through all that erosion. And so what will happen is this zircon will form. It'll be incorporated in a rock. That rock will erode away, but those little zircon crystals will be incorporated in the next generation of rocks. And so we have Earth rocks today that have these little tiny zircon crystals in them. This is a particular zircon crystal from Western Australia. And this particular one was dated to be 4.374 billion years old. That's 4,374,000,000 years old. That's how old it is. So that means the Earth has to be older than that. So we're just going to round that to 4.4 billion years. So the Earth is older than this. This makes it what we call a minimum age. The Earth is at least 4.5 billion years old, but how much older is it than that? Turns out the oldest rocks that we brought back from the moon are also about 4.4 billion years old. But the moon a long time ago, like the Earth, was geologically active, so it may be that there are just no rocks left that are older than that. So the Earth and the moon are at least 4.4 billion years old. What are other ways to determine these things? Well, we've done the same thing for Mars, and the Martian rocks are also 4 billion years old. But it turns out meteorites are the best way to do it. And the reason that meteorites are the best way to do it is that most of the meteorites that we find in space have not spent any time in a large body that's had active geology. That is, these meteorites condensed out of the solar nebula. They formed solid objects when the solar system formed, and they haven't been modified ever since. And in particular, lots of meteorites. So here are 4 different types of meteorites. There are rocky meteorites. There are iron-nickel meteorites that are made of solid iron and nickel. There are rocky metallic meteorites called pallasites. And then there are these special kinds of rocky meteorites that come from planets like Mars or even the moon. But in any case, when we look at a lot of these rocky meteorites, we see these little white spots inside them. Those little white spots are called inclusions. And we believe that those inclusions were the first things that condense out of the solar nebula. And that's because they're made of what we call refractory materials. Refractory materials are those elements that have particularly high boiling points. And so when the solar nebula starts cooling off, it is those gases that will condense to form solids first. And then those solids get incorporated in these meteorites. So we've been able to use the decay of radioactive elements to determine how old some of these inclusions are. And these meteorites come from many different parts of the solar system. So they likely date the formation of the solar system as a whole. And those inclusions inside those meteorites are 4.568 billion years old. And what's interesting is lots of different meteorites have inclusions in them. And these inclusions are, the oldest ones are 4.568 billion years old. We have yet to discover any inclusions that are older than that. There are certainly inclusions that are younger than that, but none that are older than that. And because we have lots of different meteorites from lots of different parts of the solar system, and these meteorites have never been weathered, they've never been worn down and broken down over time, it is very likely that what we are looking at with these inclusions, these little white spots, are the oldest things in the solar system. And they are 4.568 billion years old. And that tells us that is when the first things started condensing and when the planets started forming. Our solar system is 4.568 billion years old. That is a number that I do want you to memorize. I'm not going to ask you to memorize many numbers this semester, but one of the numbers I want you to memorize is that the solar system is 4.5 billion years old. You can round it to 4.6 billion years old if you would like. I should point out that this number down here, these numbers are significant. That is, the decay of radioactive elements is so accurate that we can actually tell how old these things are. This last digit down here is significant. But you don't have to memorize the whole thing. Just know that the solar system is 4.6 billion years old. So that is when our solar system formed, and that is how our solar system formed. So thank you for joining me in this lecture where we explored how and when our solar system formed. In our next lecture, we're going to take a look at the Earth as an example of a terrestrial planet. And then we will take a look at the Earth's atmosphere as an example of the atmospheres of the planets. So I will see you in the next lecture when we talk about the Earth.